A lot of stuff today. This presentation is meant to wrap it up a little bit from the perspective of the technology. So take a step back, look at the database and what makes it unique in terms of the actual features and architecture. So it's a little bit of, earlier I talked about some of the features from the perspective of the new stuff that's coming out. I'd like to take a similar view, but take a step back and look at the product a little bit more broadly. But then I'd also want to zoom out and share with you the vision for the Graph platform, what we have today and where we're going. So let's take a historical perspective. What significant thing happened in the data world in 1979? Anyone? The release of the first commercial relational database by a small company called RSI, which renamed itself to Oracle a few years later. And at the time this technology was invented, the main problem in data and the most high value bit when it came to being able to process data was to take warehouses full of these things and digitize them and get them into the system and create automated processes around it. This is why when you're in Database 101, you start with an order form, and like you can break apart the order form in order to bring it back together, break it apart, bring it back together, and that's sort of what joins are all about. And at the time, the constraints of the technology had to deal with were very small amounts of RAM. That's a 64K chip, for those of you who remember the Commodore 64 and that era. And then you have spinning platters that are low capacity, designed for sequential I/O. And whenever you're coming out with a new product, whether it's a database or a car or a rocket ship or anything else, the product is the result of what the problem is that it's important to solve and what the constraints are of the technology of the day. And what this yielded in '79 was a whole era of technologies that, as Emil said earlier, are still very useful and widely used today, and you should still keep using them. But what's actually happened since then is the world has changed a lot. And a lot of the systems that are actually really interesting and valuable to understand and analyze are systems that are dynamic and that are, involve nature and lots of interconnections and causality, and we want to try to understand them. This is why you're all here in the room today. So different kind of problem, different technology constraints as well. The technology constraints are abundant RAM, so many orders of magnitude more RAM for the same price or cheaper, and devices from a storage perspective that are much more forgiving in terms of doing random I/O. And actually, if you look at the secret sauce with Neo4j and why you can do these very fast graph traversals, it's because Emil and Johan, the co-founders of this technology, actually did the crazy thing back 10 years ago or so ago to design a database that is 100% based on random I/O. It's all just about hops. And it does that very well, but it depends on having hardware. I mean, the good thing is today this hardware is abundant and the norm. So that's yielded a new era, which we're just at the start of. A lot of you are bombarded by lots of different information about different sorts of technology, and I thought I'd provide one perspective to rationalize all of these. Like, what are the kinds of technology across your portfolio if you look at the data layer, the data storage layer? And there's a cartoon that one of my colleagues, Nigel Small, dug up that was done. Well, I'll get to the cartoon in a sec. The IT portfolio view, so one way to look at it is you have, at one hand, connected technologies, and then at the other hand, data, store and retrieve, which you could call discrete data. So I have a certain set of technologies that are designed for very high rates of store and retrieve, and then at the other extreme, you have systems designed for connected data. And the architecture trade-offs are that in order to do this really well, you need to actually give up the ability to do some of this. Like, this is what the DynamoDB paper is from Amazon, is you say, all right, let's give up ACID, let's give up the ability to do joins, let's just do key value lookups. And man, you can do a lot of key value lookups very efficiently when you give those up. But what you're giving up is actually the things that bring you more over to this side. So, which is why one of the things you'll hear us continually say is that you actually need to have different specialized technologies for handling different kinds of problems, because the problems they solve result in architectures that are antagonistic to one another. Okay, now the cartoon I promised. I thought this one actually really nicely relates how the IT portfolio view works out. You could say that from one perspective, I've got data in a database. I don't know what it is, it's just data. And there's been a lot of talk in the analytics community for the last 10 years or so about turning data into information. What does information mean? Well, it means I sort of know what color things are and how to categorize things, then I can start using them and maybe aggregate and do other fun stuff. The next step beyond that, though, is knowledge, understanding how things are connected, and then using that information in some way. But we're still not done, because if I use my knowledge to find interesting things that are only interesting because I now understand the path to get there, then that's insight. And then knowing how I got somewhere, which is following the path, is wisdom. Now let's map this back to the IT portfolio. At the far left, you have store and retrieve technologies from a transactional perspective, DynamoDB and so on. They're just taking data, storing and retrieving. And then what's this over here? This is Hadoop, MapReduce, EDWs, columnar databases, things that are designed for doing analysis of data, but not really going very deep in the connections. You might have a dimension table, and that's going one level out. You might have a snowflake table, that's going 2 levels out. That's as far as you can go in that world. Everything else is a new domain and new territory. And this is the graph databases and graph compute engines, where a graph database is more transactional and a graph compute engine does a certain kind of graph analytics, like the kinds that you heard about from Ryan with the graph algorithms. So let's summarize. I have RDBMSs and NoSQL databases that from a transactional perspective are primarily engineered for storage and retrieval. What is it that Hadoop, Spark, enterprise data warehouses do? They pretty much do filtering and aggregation, like if you sort of summarize it. They'll scan through lots of data, and they'll either find things that are outliers based on standard deviation or some sort of statistics, or they'll aggregate. And that's most of what they do. And then you have graphs, and you're starting to get the hang of this. So I'd like to drill into our solution vision and our solution portfolio. And before I do this, let me share what the different consumers are of graph information inside of the enterprise. The consumers of connected data are threefold. You have business users, applications, and data scientists. And these each map to different kinds of requirements. Applications need transactional graphs. These are your websites and so on. Data scientists need tools to be able to access the graph directly, run queries, write algorithms, run algorithms, and integrate with their existing analytics tooling. And then what do business users need? You saw it earlier with Bloom. They need discovery, visualization. It needs to be code-free. It needs to be visual, simple. And of course, that kind of visualization is part of what business users need in order to understand data and solve their problems. So this is our belief, that these are the three consumers of connected data inside of the enterprise. And what we're building out is a graph platform at the heart of which is the Neo4j database, and at the periphery of which are different tools. And now, these tools are, we're going to invest in building some of our own tools so that you can get a solution from one vendor that, and not have to coordinate lots of different technologies. On the other hand, we have a broad ecosystem of tooling providers of many technologies that you use and some that are specialized for graphs that we actually want to reveal and encourage and bring through this platform. So the platform is both intended to be a delivery mechanism for new technologies as well as a portfolio of technologies for doing visualization of a certain style, where there are lots of different ways of doing graph visualization. We have some partners that do those really well. And so the idea is to offer you some choice, but some basic out-of-the-box functionality. That's the vision. At the heart of it's the database, which has been engineered primarily for graph transactions. And let's drill into that. What are the key components of Neo4j that make it unique? Architecture components are index-free adjacency. Index-free adjacency is about when the data is written, it's connected. And I do that once, and then every time I read it, I can take advantage of that. The next one is built on an ACID foundation. There was a lot of debate around this. Now I guess that debate is maybe settled and partly understood, maybe not entirely, of does your database need to be ACID or not? And our contention has always been that with graphs, it absolutely must if you're doing graph transactions. And I'll show you a little animation later that helps explain why this is the case. Another one is to have a clustering architecture that supports graphs. What you don't, and this relates to ACID, and I'll talk more about this later. So we've made a lot of investments both in the database layer as well as in the clustering layer to make sure that the data moves rational for graphs. For example, moving entire transactions at one time, all or nothing, and they're not visible until they actually commit. We also want to make it easy to develop and easy to access the database through your application. There are a lot of great technologies these days that have a lot of capability and whose philosophy is to give you access to kind of all the bells and whistles, and you get visibility into how the technology works at a deeper level. And while it's possible to do that in Neo4j, and this is part of our open source heritage, we also understand that you only want to do that when you need to, and you shouldn't be forced to understand the low-level details of how drivers should interact with clustering, and if a machine goes down, to understand that the machine goes down and what machine to fail over to, and to try to coordinate read your own writes and passing around various bits of information between the cluster and the driver. So we've built a whole stack that does as much of that as possible for you. And it starts at the drivers and it goes all the way down through the clustering layer down into the database. There's, of course, an engine behind this that does lots of stuff. There's a Cypher aspect to the engine and kernel and transactions and so on, entirely built for graphs. And then lastly, in the same way that 10 years ago or so, we were designing for the technology future, which is here today, of lots of random I/O, being able to assume that most of your graph, most of the graph that you need to access is in memory. By the way, people will often talk about, or I guess it's possible to confuse the fact that you need a high cache hit ratio with the fact that the entire graph needs to be in memory. And those of you who've worked in the relational world for a long time know that you can actually get away with having sometimes a relatively small portion of your data set in memory at once and still maintain a very high cache hit ratio. And there are techniques across the cluster to do that, where you can send data in different data directions and have different instances with different parts of the graph warm. So there's a lot you can do to sort of stretch memory. You don't have to have all of it in the graph. And in 3.4, some of the new metrics we're announcing are to that are available are to help you tune your memory. There's a how full is the page cache to tell you whether you're under or oversized. what's your cache hit ratio at a page cache level in addition to at a query level and a transaction level. So we're continuing to with various hardware vendors on optimizations. For example, we worked quite closely with IBM on their Power 8 and soon Power 9 hardware. We obtained some pre-release Optane drives from Intel and have been ensuring that the product is able to keep up with and foresee the advancements in storage, compute, et cetera. All right, these are all important, but we only have a limited amount of time. I want to drill down to 3 of these areas. This point can't be overemphasized, that what happens as you write data, if I have this gray node, and this red node, in this relationship, when those are written together, the nodes each have a fixed ID. They each have an ID, and I can multiply that ID by an offset to find where it actually sits in memory or where it sits on disk. And the relationships at either end have that node ID actually stored, which means if I find a node, all I need to do is to find the adjacent relationship, find the node ID at the other end of that relationship, and I can just hop there. That's a pointer chasing operation, and those are incredibly cheap. You can do millions of these per second per core. Graph traversals are basically just chasing pointers, and that can only happen if at the time of insert you're capturing these pointers and knitting things together. So this is one of the key differentiators, and the result is time and time again I see our customers and our users show me charts that look something like this. So I've contrived this one, but it is meant to describe the point. That if on the right axis, on the x-axis, I can say the farther I am to the right, the bigger the data set and the more densely connected the data set, like the more average relationships per node. And then my response time is on the y-axis. That if in order to do a hop, I'm chasing through an index, which is multiple physical or logical IOs, then the farther out you go, you get this exponential growth. And once you get to about 3 hops, could be more, could be less, depending on how dense the graph is, you start exploding here. And time again, I hear stories of not only this, but the amount of processing necessary, the fact that you're doing 10 times, 100 times, 1,000 times more processing in order to join things, not only slows things down, but it makes things less efficient. So you need more and more hardware in order to grind away at the problem. And it's not unusual to see that with Neo4j you need 1/10 the hardware as you did for a previous problem, whether it's a big relational database cluster or a big Cassandra or MongoDB setup, et cetera, for these kinds of problems. I'm not suggesting that those technologies shouldn't be used for the things that they're good at. Okay, let's talk about ACID. What does this actually mean? When we say ACID consistency for a graph, it means that if I have a subgraph could be as small as a single relationship, and then I need to go update the node, update the other node, create the relationship, update the properties, and then maybe update an index. All of that should happen on an all or nothing basis. Here you have 5 nodes and a bunch of relationships. That all needs to happen on an all or nothing basis, and it needs to replicate such that it is either visible or invisible as you go. And then if you can't reach quorum, then it needs to roll back or not occur so that you don't end up with a situation of having branched data and these machines disagree with each other. This is why we have ACID built into the database. This is why we use Raft, and this is why when we replicate amongst database servers, the transactions all move on an all or nothing basis. So why is this important? Let's look at what happens if you don't do that. Let's say you take a graph layer and you build it on top of an eventually consistent database that's designed for key values or column families or something else. Well, when I hit my first server, this graph is going to be decomposed into a bunch of different rows, right? And those rows are each different units of work, and to the degree that maybe Cassandra supports a lightweight transaction, it is for that column family, which means if this turns into 5 column families, I can have the situation where as it's going, it'll commit in different orders, and some of these might fail in the worst case scenario. Usually they don't, but every now and then some of these might fail, and you might actually end up in that case with a relationship that points nowhere, and that kind of corruption can cascade in the graph. What can happen more frequently is if you have a high write throughput, then as this thing is going through, I can have reads coming against this, and you'll read half transactions, which is problematic. And then when I propagate, same problem, you can end up with a problem of having partially committed transactions where part of it succeeds, part of it fails, or more likely, or more commonly, your read will come in and view a half-committed transactions, and then it'll return wrong data, and that can corrupt the graph over time. Does this make sense? This is something that my observation on looking at the amount of interest there is in the space for technologies that do this stuff on the right is that people don't understand this. And we've actually had customers who've either tried to build something or used some graph layer that accesses Cassandra or DynamoDB or something on the back end, and have actually run themselves into some serious data problems once they're in production, because you take this for granted. Like our muscle memory is that databases are trustable. We have had that for a long time with relational databases, and it becomes nuanced when you work with relationships. Okay, another element is Cypher. You've seen this one before. Possibly you've seen a lot of this today. But time and time again, I see cases where you have massive SQL queries, and then the equivalent graph query looks like this. And the productivity impact is kind of obvious. I'm not going to spend half a day writing this or more, and then another half day or a couple days testing this. But then once the thing actually works, it's going to take a long time to run. Okay, let's say I've gotten through those hurdles. My next step is 6 months later now, someone's asked me to go and change the logic in this query. Now I need to figure out what the heck I did. I wouldn't remember what I did here. So it's less time debugging, code that's easier to read for you or other people that may inherit your code. So that's another value. And as Ryan mentioned, Cypher is something that we feel is so valuable and so important for the space and for the community that in late 2015, we actually opened this up as a baseline for an industry graph query language. And if you go to opencypher.org, you'll see a lot of design activity happening in the open with a lot of participation from other players, and things like spatial, things like composable graphs, which I'll talk about towards the end of my presentation, are all emerging. You're all welcome to participate in that, by the way, if you're interested in how database query languages evolve, or you want to provide feedback, we really welcome participation. And then you've seen this one, just the impact of the conceptual, logical, physical, all mapping and being the same. One of the impacts here is that, and the first time I heard this was from Kurt. Where are you, Kurt? Yes. Kurt is on the PM team at Neo4j, one of my colleagues, who, when the first talk I ever heard him give was when he was a Neo4j customer at Crunchbase, heading up product and engineering there. And a point that he made was that the impact of this isn't just that the first project is faster, it's that the second project is much faster, and the third project is much faster, because you don't need to refactor and do schema migrations. You just add things on as they come. I don't know if you remember saying that. Yeah. All right, so that's graph transactions. That's Neo4j in a nutshell. Let's talk about analytics. Graph algorithms are one important class of graph analytics, and then the other class of graph analytics are queries that can be expressed in Cypher, but that are more globally oriented. Graph algorithms, we have this library, it's out there, you can go grab it, try it out, and there are a number of different kinds of graph algorithms. 3 kinds that we support today are pathfinding, centrality, community detection. And what all these have in common is they will run iteratively through large parts of the graph, possibly the entire graph, and compute things and come back with some answer. I heard a podcast recently where a VC who is very focused on AI described community detection as an important pillar in AI as being something he was describing as end-of-theory AI, which was one of the 3 types of AIs as he defined them, is in some ways this comes close to living up to this promise that technology software vendors have never really been able to live up to, which is the technology will answer questions that you haven't asked yet. That's not exactly true because you're saying, give me my communities. But what it finds is going to be very unexpected. And there are different ways to ask the question where the communities can be more or less granular or based on different kinds of relationships, different things. So this is an important and valuable tool, and we've tried to make them relatively easy to use because the math behind these is quite complicated, but you don't actually need to understand that all that much in order to run it and get value. Centrality, the famous one is what? PageRank, which was Google's innovation, which differentiated them from Lycos and AltaVista and all these other search engines back in the day by ranking your search results based on the number of inbound links. But it's actually not just the number of inbound links, it's the number of weighted inbound links. So you iterate multiple times and you converge. One of the technologies that is out there that's commonly used for graph algorithms is GraphX. If your data is already in Spark, that's a reasonable thing to use. If your data is in Neo4j, then it's nice to be able to just do it directly in Neo4j, not having to export it to Spark. So the graph algorithms in Neo4j compare quite well with the GraphX timings. These are able to be quite grabby in terms of machine resources. We design them so that you can, if you have 100+ cores on your machine, it'll use 100+ cores. And we, just before going live with these, we did a billion relationship PageRank across a payment graph from a large payment provider, and that ran in 10 minutes on a 100+ core machine. Of course, not all of you have 100+ core machines, so maybe it'll take 100 minutes if you have 10 kind of thing. So I want to highlight an aspect that I believe is very important with respect to AI, which is this virtuous cycle between analytics and transactions. I actually think that if you can close the loop between those things and effectively take the data that comes out of your transactional systems, analyze it efficiently, come out with algorithms that then feed back in the transactional system and use those, then you've created something very powerful. I love Michael's earlier perspective on what EY is doing with knowledge graphs and with AI. We have our own perspective on this that actually overlaps quite a bit. And this is a young space where everybody's trying to figure out AI and the technologies are evolving very quickly. So this is, I'm going to walk through quickly where we see Neo4j being used today in AI and possibly more in the future. But take this as inspiration because I'd love for one of you to come out with a 7th, 8th, 9th approach here, or saying, number 5 is no good, try something else. That'd be great. There's a lot of room for evolution here. Knowledge graphs is a key one, understanding going from words to meaning, and the meaning through relationships and through knowledge representations. That's a key area in AI. These two go hand in hand, graph-enhanced AI models on the execution and learning side. So you can imagine the input to something like TensorFlow is just a bunch of vectors, right? You have you have a very wide row with lots of columns. So how do I give that graph input? Well, there are a few ways. One is you could feed it the result of a graph algorithm. You could feed it a PageRank. You could feed it a community out of community detection. What you could also do is you could tie it back to a transactional query and say, I'm going to have 3 Booleans, each one of which represents, is this person 1, 2, 3 hops out from a known fraudster? And then you feed that into the machine learning algorithm, and it figures out whether 1, 2, 3 hops out is an important signal. And if it is, then you can use that on the execution side. And what that means is when you execute your TensorFlow, you need to run a 3-hop graph query, and Neo4j is really good at that, at doing that on the fly and sending it in. Graph analytics, we just talked about. Having a system of record. A lot of these AI activities require pulling data in from all these different sources and joining them together, and then oftentimes you'll do your analysis and you're done. There's no place to put the data and store the relationships, and then you start over, like you have your next exercise. I have a customer who once likened this to, he'll build a 30-story building, and then the next day he needs to build a 31-story building, but he needs to start from the ground floor, foundation up. Neo4j is your graph system of record for the connections, perhaps in concert with a system of record inside the Hadoop ecosystem for all of your transactions, can actually work pretty well for saving time and gaining efficiency. And then the last one is understanding why the machine made the decision. Now, don't get me wrong, I don't think it's particularly useful to actually go inside of a neural network and try to visualize that. That'd probably be about as useful as trying to understand what someone is thinking by doing an fMRI of their brain. However, it's probably useful if you have a decision tree where and you have the history of a decision tree stored in the graph, and you actually want to explain to someone why their mortgage was approved and denied based on a particular set of rules that existed 6 months ago. So there's a lot of promise here with the visualization technologies combined with storing your rules in the graph. Let's talk about data integration. No database exists in isolation. Every database needs to shuffle data to and from different systems in batch, in real time, and integrate with different tools. Some of the common integration patterns that you see are, one, just going from a tabular system into Neo4j. Another one is going from having multiple systems and having Neo4j map the connections. Once upon a time, I co-founded an MDM startup before the term MDM was really out there. And at the time, there was this big debate between, well, should you just force all these systems into one system of truth, or should you leave them as is and have some service bus and do it all through an SOA layer? And actually, the right answer is, from what I've seen, is it's somewhere in between. You use a graph database to knit together all the key identifiers and possibly just a thin sliver of things beyond the identifiers that you might want to use in a query, so that as data comes in, you can direct it to the appropriate system. Because at the end of the day, these systems all have their own different definitions for valid business reasons, and you can't really force those things together. They have different SLAs as well. And then last but not least, another common one is getting data out of the analytics system. One characteristic of data lakes is people oftentimes will use them as a data dumping ground, and that's kind of what they're designed for. And you don't want to do that with a transactional system, whether it's graph or relational or anything else. If there are a lot of transactions that are uninteresting, and then there are some that are interesting, or you have some transactions that are interesting in the aggregate, then you can actually use your data lake to pre-aggregate or to identify things and load it into Neo4j. And you heard about this with the eBay virtual browse nodes use case earlier. So these are all areas that are very common and where there are increasingly partner technologies and where we're also building out some solutions ourselves. Drivers and APIs, there's quite a lot there. in terms of official drivers supported by Neo4j. Right now we support Java, .NET, Python, and JavaScript to the level I was describing earlier, just supporting the Bolt binary protocol, knowing all about causal clustering. We're working on additional languages, and there are some good drivers built by the community as well. Next, discovery and visualization. You heard all about this, but I'm going to give you a little bit of a classification scheme here. One is, okay, you have development tooling, which is not really end-user visualization tooling, and that's useful and inspiring, but it only goes so far. And in some cases, you'll have applications maybe used by a department where the business user has lots of dashboards and lots of functionality, and you don't want to give that user a separate tool. You want to give them a visualization as part of the universe that they live in day to day. In that case, you need to build something yourself. And we, as well as many of our SI partners, have developed a lot of competencies in helping to guide and build out these applications. So if you need help with something like that, that's one of the things that we can help with, that Michael and team from EY can help with, and others. There are also some other companies out there, Linkurious, Tom Sawyer, Cambridge Intelligence, that have built their own graph visualization tools that each have their own perspective and way of doing things. And then you'll soon have Bloom, which I mentioned. And I believe our job as a platform vendor is to give you as much choice as possible, because every need is different, every application is different, and we intend to continue supporting all these different methods. Development and administration, I talked about the Neo4j browser earlier and the desktop, so I won't spend much more time there, just out of time. This last area, analytics tooling, I haven't said a lot about, and I'll linger on a bit. One of the projects that we've been working on is building Cypher support for Apache Spark, so you can actually go into your Hadoop environment and run Cypher queries. This can be super useful from a bunch of perspectives, including being able to take your data, massage it, evaluate, pre-compute, and then bring data into a transactional graph, or backtest algorithms, or any number of other use cases. In the same way that SQL is a first-class citizen within Spark, we believe Spark should have a declarative graph query language as a first-class citizen. And we've been working towards this. So what you can actually see, it's a bit small, is the same Cypher query running on Spark and running in Neo4j in our lab. The project is out there. Feel free to check it out. It's on GitHub under the OpenCypher owner. And this is the vision for that you'll have a relational view and a graph view, and you'll be able to interchange those views and have different languages accessing the same data set. And we're not far from actualizing this. And then a last aspect of this, not to be overlooked, is one of the advancements in the Cypher query language is to allow Cypher to return an in-memory graph representation. So I can have a graph of people with their friendships, and let's say all I care about is friends of friends or friends of friends of friends. I can run a Cypher query that extracts the whole graph and converts it into people and an FOF line, and skipping the middle node. And then you want to be able to operate on that and operate on that. So we're actually designing Cypher in the next generation iteration, Cypher 10, it's versioned, to be able to return graphs and operate on in-memory graphs. And this is one of the capabilities that we're targeting first in Spark, and then we'll target in Neo4j. Okay, so in summary, the platform means better access to technology partner software, and we'll be announcing more ways to do that later in the year, as well as new Neo4j provided capabilities. So when you look at Neo4j, be sure to look at it not just as the database or not just as the technologies that we provide, but the community, the overall ecosystem, education, partners, solutions, et cetera. Thanks. So,